Today we are going to discuss about the molecular term symbol lecture 2. In this lecture we will discuss about the diatomic molecular term symbols and the reflection through a plane in the molecule. Term symbols of diatomic molecules. The first step is to determine molecular term symbol. We first calculate the possible values for the total orbital angular momentum, that is capital ML, which is the sum of the orbital angular momentum of the electrons occupying the molecular orbitals. Now to calculate the capital ML is equal to small ml1, small ml2 plus etc. Small ll1 is equal to 0 for sigma orbitals, small l is equal to plus minus 1 for a pi orbital, and so on. So ml is the projection of units h bar of the orbital angular momentum on the z-axis. Different electron configurations give rise to different allowed values of ml. This h bar is equal to h upon 2 pi. Where h is the Planck's constant, but here this h bar is known as the reduced Planck's constant. Now the various values of this ml, modulus ml, are associated with capital Greek letters according to, if ml is equal to 0, then the symbol will be sigma. If ml is equal to 1, the symbol will be pi, 2, delta, 3, it is phi. Once ml has been determined, we then determine the possible values for the total spin angular momentum. This is the second step. So ms, capital MS is equal to ms1 plus ms2 plus etc. The values of ms correspond to the projection of the total spin s of the molecule along the bond axis. Now if ms is equal to 0, then s will be 0. If ms is equal to plus minus half, it is ms is taken as half only. If ms is equal to plus minus 1, this is 1 is taken here. Hence the total spin s can be determined from the obtained values of ms. As mentioned above, the symmetries and parities are different between a heteronuclear diatomic molecule and a homonuclear one. Their term symbols usually have different formats. For homonuclear diatomics, the term symbol has the following forms, that is, this is the spin multiplicity upper left, and this is the lower right, this is omega. So this is the lambda. This is lambda will show us about the symbols, and this omega is the parity, that is G and U, and this plus minus sign is the symmetry upon the reflection of an plane passing through the nuclear axis. Here again, whereas lambda is the projection of the orbital angular momentum along the internuclear axis. Omega is G, either G or U, that is parity, and plus and minus is the reflection symmetry along an arbitrary plane containing the internuclear axis. Lambda may be one of the Greek letters in the sequence sigma, pi, delta, and phi, where delta is equal to lambda, where lambda is equal to 0, 1, 2, 3. It is similar to in the atomic term symbol, where S symbol is taken here, sigma. There are an infinite number of planes containing the internuclear axis, hence there are an infinite number of possible reflections. For diatomic molecules, the planes are infinite. For any of these planes, molecular term symbol with to more than 0 always have the state which is symmetrical with respect to this reflection and one state that is antisymmetric. Rather than labeling those situations, that is pi plus minus 1, the plus minus omitted. It means in pi orbitals or in d orbitals, the reflection will be symmetrical and asymmetrical both, so the plus minus sign is taken, so this is omitted. Only in sigma orbitals, that is pi is equal to 0, the only either plus or either minus is used. For sigma states, however, this top fault degeneracy disappears, that is plus minus, and all sigma states are either symmetric under any plane containing the internuclear axis or antisymmetric. So in sigma there will be either the symmetric or asymmetric. These two situations are labeled as this is for symmetric, this is for asymmetric. This here we can explain more that how this is there. So suppose this is the sigma, 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 sigma. In these, the plane passing through these, that is from front to back, it will be symmetrical because same phase are in the reflection. Here will be the same phase. If we take the plane from upward to downward like this, again it is symmetrical because the same after reflection the same phase is there and same phase is there. So in sigma here the either plus or minus, so this will be plus, this will be plus, this will be plus. So in pi orbitals, the suppose this is the orbital, if this plane we take, then this is the asymmetric because there here and here, these are the two different phases. So this is one is the asymmetric. But if we take the plane like this, then this will be the symmetric because it will cut half of this, that is same phase, and this is the also same phase. And in this the pi orbital, again plus or minus both are possible. If we take this plane, then it is the symmetrical because they are bisecting the orbitals in this way. And if we take from upper to lower plane, this will be the asymmetric. So this is the plus or minus, this is the minus, and this is the plus. So we can explain that in pi orbitals there is plus or minus, both symmetries are there, and in sigma orbitals it will be either plus or either minus.